Hello, everyone, and welcome to today's session. We hope everyone is doing great. My name is Duman Mana. I am a petroleum engineer working as a field engineer with Halliburton, Iraq, and I'm going to be your moderator for today's session. On behalf of Arab Oil and Gas Academy, we are happy to have you here with us today for the webinar Challenges of Handling Sand and Gas in Artificially Lifted Wells. Now, I would like to present our speakers for today. First, Dr. Mohamed Ghareeb. Dr. Ghareeb has PhD in petroleum production engineering with specialty in artificial lift and production engineering and operation. He is currently teaching in Egypt, Future University and New Cairo Technological University. Meanwhile, he is Global Technical Director, Artificial Lift System for United Lift Technologies. He has 34 years of experience in the industry, ranging from business development, sales, marketing, operation, teaching and applications engineering, covering artificial lift design for major service companies such as GE and Weatherford, and oil field operations for major operators such as Eni and GPC. Dr. Ghareeb has field experience in artificial lift systems in Middle East, North Africa, Russia, Turkey, and so on. Over the past years, he also has played a major role in the practical training for the field staff and engineering in oil and gas production engineering and well operations for different major companies in the MENA, USA, Canada, Romania, Turkey, and Far East. He was SPE Egyptian Section President, Program and Membership Chairperson. Also, he is the Membership Chairperson and Director of SPE International Artificial Lift and Gas Well Disqualification Technical Section. He published and presented over 55 technical papers. Currently, he is committee member for ATCE 2020 and 2021 SPE Middle East Artificial Lift Conference. Dr. Ghareeb is 2011 and 2020 recipients of the SPE Regional Technical Award in Production and Operation. Joining him in this session is Engineer Gustavo. Engineer Gustavo is an industrial engineer working as a professional in the oil and gas industry for 10 years. Throughout these years, he was dealing with different production and completion practices. These practices have mainly involved finding and developing solutions, as well as designing bottom hole assembly for severe sand, gas, and corrosion issues. For different artificial lift systems, along with working in production disciplines of the upstream oil and gas industry. He also have gained the experience of leading and managing technical and engineering department at Odessa Separator. He has also been involved with SPE, currently have 6 SPE papers, 14 SWPSC papers, and 4 patents. Now, before we begin, let me remind you that this session is being recorded. If you have any question, please leave it in the Q&A box down below. And now, please help me to welcome Dr. Ghareeb first. Dr. Ghareeb, it's a pleasure having you here today with us, and the mic is yours.
Thank you, Rahman. Good morning, good afternoon, everyone. Just because I know from different place, from different area. We are presented before almost more than 11 webinars about artificial lift and artificial lift technology, and we cover all subjects. Today, really, I like just with Gustavo, with the help of Gustavo and Odessa separators, just to present some of the main challenge facing the artificial lift application and operation and design. It's the sand, gas, corrosions, and so on. These 3 of the main challenge. There is some other more challenge like depth, deviated temperature, and so. But however, gas, sand, corrosion is the major problem for all type of artificial lift, regardless is a pumping or just gassing, assist, helping, or whatever. This is a main problem. I will start just with a couple of slides hinting, just to introduce you about sand, gas, what we need, just to open the floor to Gustavo, because Gustavo have a wide experience in this area. And Odessa Separator have a great technology is solving such a problem, or overcoming problem, or reduce the harmful of this problem, and so on. The agenda will be about, I give you some introduction, and then if someone have some Q&A related general artificial for 5-10 minutes, I can answer. It's no problem. About all the previous webinars, I already did it, and you already downloaded from the YouTubes, and you listen to them, If not, I will just give you some hint about sand, gas. What sand? What gas? What's the problem of sand? What's the problem of sand? At the high levels problem, top, just general overview, to brainstorming you, to open the floor to discuss Gustavo again. Then I will leave the floor to Gustavo for our main presentation today. He will present it this solution for sand, gas, corrosions, how to, to mitigate this problem, or just to allow the artificial lift to work in a very good efficiency or high efficiency on such type of wells suffering from this problem. At the end, we'll have some session, Q&A sessions, you can ask for Gustavo, mainly for Gustavo, and also I am here, if something related to my slides or something like that. Technology of artificial lift, as we are presented before, this is a technology what we plan, just to cover today, We plan to cover, when we talk about artificial lift technology, we talk about general. We are not talking really about one type of artificial lift. Today, we will plan to present sand, gas, corrosion problem for all types of artificial lift. You can ask your question about all types of artificial lift, either mechanical assist, like the right-hand types, or just pressure or formation assist, gas assist, whatever, like gas lift, foam, plunger lift, and so on. Then, just let us say, gas, sand, corrosion as overview. Why are sand and gas and corrosions is a problem? Why is a problem for artificial lift? Not only for artificial lift. Why is a problem for oil wells? Not only oil wells, even gas wells, all type of wells, even water wells, if you are producing from water wells or just injecting to water wells. Sand, gas, corrosion, especially sand and corrosion and gas, really, it's a big problem. How to recognize the problem? From a target for our presentation today, from Gustavo presentation, you will know how to recognize your problem. Is really you have a problem of sand? Is really sand creating a problem for you? How to solve? How to overcome? Do you need to bumping the sand? Do you need to separate the sand? What you need to do? This is just one hint you need just to focus while we are presenting our presentation today. What's the solution available in the market? If there is one solution, two solution, or just combined solution even, is a solution in separation of this problem, sand, gas, or just bumping this problem? If separation, what's the related other problem? If bumping, what could be also the problem? When to do what? As a general rules, when to do what for gas, for sand, for corrosion, and really some, in many fuels, you have combination of that. You have fuel produced sand with gas, corrosion environment, you have corrosive H2S, CO2, whatever. You can have a combination of that. What you need to do? What's the general rule of thumb? Do you need to look for sand only, for gas? If we need to look for sand and gas, what about corrosion? If the corrosion presence, you need to have an overalls, just solution for the well. Is available for all solution? Yes. Today we'll talk about one subject only, as a separations for this, or just a treatment for this. But in the market, there is a lot of other solution from manufacturing of the equipment, downhole pumps. What type of pumps you need to use for gas? ESP pumps, PCP pumps, road lift pumps. Even if you are separated, what type of pump do you need to have? You are not able to separate a complete sand, or just a complete gas. Could be gas sometimes with some special completion, and so you can do it. What solution available? What we need to do, and so on. Then let us just give you some hint about sand problem, general speaking, I will not talk in detail. I will leave all that to Gustavo to go in details for that. But I give to you general, to open mind, just to let you know when Gustavo talking what you need to focus more, what you need to have, and so on. Usually sand in the wells coming from, in general, in general, coming from reservoir or sand frac. Sometimes after frac, you have frac probe and sands probe from the frac, or it's coming from reservoir. If it's from frac, usually we can consider, in general as a temporary, because frac, sand comes from frac, you need to clean that with whatever you have, and you need to pumping or get out well. Even after you clean the wells, before you run your artificial lift, there is still some of frac coming from the formation or from the well. But we consider this as the temporary, and the well can be cleaned with the time himself. The major problem is the sand come from reservoir. Sand come from reservoir, it's ongoing problems, special problems. And, this is, do you need to leave the sand downhole by separation, or you need just to pump the sand, or you need just to, to optimize. Some of the sand you can leave it downhole, some of the sand you can produce. In both cases, there is a problem. Either to separate the sand, you need to have, there is some problem. You need to pump the sand, there is some problem. What type of solution I need to have? How to optimize my operation? At the end, we are in oil and gas, for a business. To produce the wells, the cost per barrel, with the lifting cost to be optimum lifting cost, We are in just as I said, in oil and gas, we are in the business. Generally speaking, what are the problems associated with the sand production? Sand and solid, when we talk about sand, we talk about sand and solids. In oil and gas, well, generally speaking, it creates serious problem for especially pumped artificial lift wells, pumped wells. Maybe for gas lift, for some wells, like jet pump, some other have no moving parts. Maybe the problem is not severe, but still a problem. But for pumping wells, it's a serious problem, especially for road lift, especially for ESP and so on. What this happens, this will be, will affect an overall production and safety. Production, yes, it can creating a low production. It can reducing my volumetric efficiency, mechanical efficiency. Safety, yes, safety related to operation. Because since you have sand, you have gas, the amount of operation failures maybe would be higher than the normal wells. Then doing some workover, some surfacing, some cleaning, some operation, there's a safety hazards. When you are reducing that, you are improving that. Sand, solids, whatever you have produced or just post together, create common operation problem. I will just mention some, maybe more and more than that, Like what, Like it can form a bridge in the casing tubing annulus with the sand. If you start to separate the sand, where is the sand will be go, Even if you start not separated the sand, the heavy particle of sand with low production wells will settle down. This restricting flow to the pump intake. If you restrict flow to the pump intake, then you're restricting your capability to produce your flow. Not only that, this can be also if you start to cover some of your reservoir perforation and so it will affect on reservoir inflow from reservoir to the well pool, You are losing your subsurface pump mechanical efficiency, especially for the sand. And here I talk about sand. Sand start to create some corrosion, some erosions, problems, some failure for some parts. Then your mechanical efficiency with time will go down, Losing mechanical efficiency, this can be a big problem for your system. For example, for ESP wells, you can have an excessive pump stage wear, and also elevated the pump shaft vibrations will be increased the vibration for pump shaft. All that is a major problem for ESP wells, For road lift system, there is plenty of problem, like sticking a plunger in the barrels, Sticking a plunger in the barrel and cutting the plunger of the pump and creating a lot of slippage in that pumps. This will reducing the mechanical problem, and the pump can lose its efficiency. For PCB pump, even for PCB pump slugs can fill PCB pump cavities because the PCB pump works with cavity, resulting in excessive torque because the PCB pump running by rotation, and the torque is transferred to the pump by the rod or just by the ESP motor downhole. There will be more torques on this carrier. It can make downhole equipment removable difficult. Sometimes if you have a sand and the sand settle over the bump, especially like insert bumps, for road lift, for insert BCP or ESP or whatever, if the sand accumulated over the bump, it's not an easy to remove the bump or just to retrieve the bump from the wells and so on, more frequent maintenance from time to time. You need to retrieve the bump, change the bump, clean the downholes, clean the wells from the sand and so on. Then this will be a more operating cost, there more lifting cost and so on. This just as a general, there is more than that and so on. What in general solution, I am not talk about now detailed solution, but I give you philosophy, general rule of thumbs, what we need to do if I have solids and sand for these wells, what I need to know. First of all, you need to separate us. You need the best way for you to avoid solids or sand, a challenge to prevent them from entering the downhole lifting equipment, whatever type of downhole lifting equipment. This is the first place. In the first place, downhole, you need to separate it. But sometimes I cannot separate complete sands. Sometimes the sand is very fine sand. If I start to separate it, maybe I plug the intake. Gustavo can give us some hints about that, what is it. But separation of sands, it's one of the good solution downhole. And from time to time, you can clean the well. It's not only for the downhole bump, even separation of the sand will also help you just to minimize problem for surface equipment, because producing sand sometimes also, it's not all sometimes, it can create a problem for separators, for pipelines and so. Then separating sand, and from time to time, especially if you have a good rat holes, that's the distance below the bottom perforation. Then from time to time, you can cleaning sand with coil tubing, with flash bar units and so on, clean and so on. Then we can eliminate it, some even of surface problem and downhole problem. Second, bumping. I need to bumping, just separating, and also sometimes I need to bumping, especially very fine sand, there is in the market a very wide range of bump configuration for ESP, for PCP, for road lift, whatever type. There is a very wide range of bumps and fittings for that bump. There is a technology can be used, to handling a very high percentage of sand, At the end, usually you are doing as a commonly use a combination, separation and bumping, separation a certain particle, certain size of the sand and so on, and then bumping the other side. This will be eliminating the problem for separation and for lifting the bumps and so on. Some other general hints about gas problem, and especially for the petroleum engineering, I will try just to highlight 2-3 slides here about petroleum engineering, and the one who designed the artificial lift system, the one who's operating the artificial lift system, especially bumping system, what you need to consider, and so on. Generally speaking, gas continues to be one of the major contribution to low volumetric efficiency, because the gas occupied a part of the pump volume downhole. You run the pump downhole just to lift liquids, not to lift the gas. But if you have the gas, then the gas accumulated a part of that pump, then the part of the pump is used to lift the gas. Then your volumetric efficiency proportionally will be less based on the volume of gas you are pumping in. Pumping free gas significantly decreases, as I say, not only volumetric efficiency for the pump, the total system efficiency. Total system efficiency, for example, for the road lift system can be reached to 50-55%. If I start to produce gas with the pump and the pump fill with gas and so on, the volumetric efficiency decrease and the total system efficiency can be 35%, 40%, and so on. Then I use more power to lift same volume of fluid, total fluid, and so on. This directly also contribution to high lifting cost at the end, as well as indirectly contribution to the deteriorations of subsurface equipment, damage of equipment, like cavitations. If you have a cavitation in the pumps, if you have a gas lock in the pump, you have bounding fluids, bounding gas for the road lift, and so on. All that's just some problem. When you design artificial lift, usually this is a starting point. This is a willing flow performance. All the engineers, or just most of us, just when you start to design the system, we design the system based on the well inflow performance. Remember, the well inflow performance is a relationship between the bottom hole flow pressure and the stock tank flow rates. That's mean this is the blue one, the dark blue curve is the stock tank flow rates. When the engineers start to look about the pump, look, the pump is working downhole. It's not work at the surface. Then you need to consider the fluids at the pump condition. What you have if the gas come out of solution? Majority of the road lift or just of the artificial lift system, you need to maximize production. When you are maximizing production, you need to maximize your drawdown if there is not create a problem for reservoir. Maximizing drawdown, that means you're reducing the bottom hole flow pressure. And in most cases, you go below the bubble point. If you go below the bubble point, if this is a bubble point, if you go below the bubble point, then the gas come out of solution. Then the curve, this represent oil at the pump condition or just liquid at the pump condition plus the gas, liquid plus the gas. When the gas, the pressure over the gas start to decrease the pressure according to the gas low, then the gas volume will increase too much. At a certain point, certain pressure, the gas volume will be very high. You want to reduce this amount of fluids at the tank. For example, if you have bottom hole flow pressure just over the pump, it's 200 psi, you can produce around 550 barrel per day as a tank. In order to produce this 550 barrel per day at the tank, you need your pump to pump down only liquids. If it's only liquids, 600 barrel per day. What if I pumping also the gas at this 200 barrel per day? Then I need to lift around 850 barrels of total volume. To reach 500 in the tank, I need to lifting another 300 barrel per day with me if I want to lift the amount of gas. This is not even a very high gas liquid ratio once. Then we need to separate a part of this gas in order to have a good efficiency. How much you separate? You separate 25% of this gas, separated and venting to the anions, then you need to produce your pump to pumping this total liquids, and then in order to produce to the tank this liquid, you need to separate 50% of the pump of the gas. You need to present just to separate this amount of total volume of free gas as a pump and take. However, you need to consider how much gas I need to separate. It's not an easy to say how much gas. You separate gas and then you need to vent gas in the casing. Is allowed to vent the gas in the casing? How to vent the gas in the casing? How the efficiency of lifting the gas to the casing? I take one example from one wells. I did a study for these wells, and I show to the engineers. When you start to design, and some of the engineers say, okay, I need to design the well just to maximum production the well. I need 200 barrel per 2,000 psi as a pump intake pressure is high. Still 2,000 over the pump. I need just to produce with 50,000 barrel per day and so on. In order to do that, what will be the problem? How much volume of gas you need to lift? How much volume of gas you need to separate for this case? Especially in this area, if you start to produce below the bubble point pressure, look to this area. The curve, this curve of this area is depend on the bubble point pressure and the amount of gas in solution, how much gas in solution. When the volume of gas in solution is increased, this curve will be more sharp, can be in this case or can be like in this case. Then whatever you reduce in your bottom hole flow pressures, the amount of gaining fluids will not be too much. Yes, you'll gain few barrels, but you need, in order to gain these few barrels, you need to lift maybe 100 barrels of just complete fluid, gas plus liquids. We did some design for this well, and we say, okay, what if I set the pump as a perforation? What if I have my pump intake pressure 300 psi? Against, if I reduce my pump intake pressure to 50 psi, my managers and the company management say, no, you have 300 psi above the pump and you still leave some fluid in the wells, you need to pump more. Sometimes I reduce the bottom hole flow pressure and I will reduce the production. How come like that? If the pump intake pressure, for example, 300 psi, the amount of fluids to produce from here, liquids at the tank, stock tank, bank tank, will be 243 barrels per day as a tank. If I reduce to 50 for a well like this, I will gain few, just how much, it's 14 barrel per day. And if at this condition, according to the BVT data for that wells, the RS is 81, and here is RS is 28, because I reduce about 250 psi. Then this is a beta gas, this is a beta O, just to convert. Volume of oil as a pump condition and bottom hole condition at this condition is 267. Volume of the pump and this of the liquid of oil will be 276. What is the volume of gas? Because there will be a gas separation here. See the volume of gas, how much? Here will be 1,120 barrels. Here will be 832 barrels. Just, amount of gas. Just only 50% of this gas, 82 barrels per day. 50% of this just amount of gas will be 52 barrels. Here it will be 420 barrels. In order to lift, to gain these 14 barrels, I need to lift almost here about more than 360 barrels per day. Then I need to increase your pumping parameters, whatever ESP road lift system. Increasing pumping parameters sometimes not gaining more production. You are reducing more powers. You are reducing more stress in the equipment and so on. Then when you start to look to your well, either optimization or just design and so, look to your type of inflow. Is your type of flow below bubble point in this, like in this curve, or in this curve, or in this curve? This is the worst case, worst condition. Whatever I go from 2,000 to 500 barrels per day, how much oil I gain, but how much gas will be separated in this case, and so on. Then, general speaking, for gas, recommended strategy as a general strategy for gas and competing with gas, what we need to do. First of all, you need just to try to avoid gas in well pool from entering the pump. How to avoid gas? If I have a good reservoir, good high productivity wells, low bubble point pressures, and so on, or just have a very high productivity, and so on. Run the pump with a pump intake above the bubble point, 20, 30, 50 psi is okay. Or avoiding by run the pump intake at the point below the perforation. If you run pump intake below the perforation, then usually the gas have a tendency to go up. However, one of your strategy, when you design, when you're selecting your equipment, try to put in your mind how to avoid gas entering to the downhole equipment. If you are able to do that without affecting in your production, in your system. If not, then you need to separate the gas from the fluid mixtures. You need to do a separation, and in order to do a separation, you need to have a good annulus, the clearance between casing and tubing venting efficiency. The wellhead valve should be open. The wellhead pressures at the casing should be minimum as much as you can. And also, you can combine this sometimes, in most cases, maybe I'm not able to separate a complete gas. Then I need to have some process. I need to have some process of how to handle the remaining of the gas with a pump. What technology was a pump required to handle this extra presence of gas, like for ESP, special stage, special configuration of impellers and diffuser, and so on, for road lift, special type of pumps, and so on. At the end, try to control how to control the gas entering to the pump by optimization and so on. Just 2 slides about corrosion and mean corrosion and so on. Corrosion is a complicated. It's not easy just, to present it in 1, 2, 3, 4 slides. Because corrosion, there is a plenty of source of corrosion. There is a different type of corrosion. Where is corrosion present, at what type of pressure, at what partial pressure, and so on. Then corrosion is a complicated subject, and often sometimes it's misunderstood. What corrosion was, what I need to do. In most cases, I need to consult expert in the corrosions, just to help with me what I need to do. There are many different corrosion problems, existing downhole, can be affecting the tubing and roads and pump configuration, even in the PCB elastomers and so on. Acid corrosion is one of the most common corrosion. What is the most common problem? H2S and CO2 are also the most common, and NES, if you want to go and just have some good guidance about corrosion, how to deal with the corrosion, what type of metallurgy, what type of materials you need to have, and so on. I recommend to go to NAS guidelines to just, to help you in that, Scale, one of the major problem can be creating or just can be plugged your pump intakes, pump intake, and even can create more problem for frictions and so on. Chemical treatment is a critical point, but chemical treatment is expensive. How to do chemical treatment? Do I need chemical treatment at surface? Do I need chemical treatment downhole? What's the best efficiency? And what's the more economics chemical treatments for my wells and my condition and so on. This is just a hint, a general overview about sand gas corrosion before, Gustavo give us more details about solutions, how to do that, and what's the solution in the market, what Odessa separators is presenting to the market solution. If possible, he can give us some case histories or something like that. Thank you, Loma. I don't know if there's 1, 2, 3 questions I can answer quickly. If not, I can keep it to the end.
Thank you, Doctor. Okay, one question. What's the possible solution to the problems corrosion in the borehole?
Yeah, corrosion, as I said, if you have the corrosion problem, first of all, downhole corrosion problem, you need to treat the problem from downhole, because usually majority of people start to treat with the equipment in the surface. Then you need to either inject chemical in the hole. Injecting chemical in the hole, really, it's not an easy. You need to run some chemical downhole. You run like a capillary tube, small capillary tube to inject downhole. Or there is some solutions like what Odessa will present. They run what you call solids chemical, slow release chemical downhole. Then you need to treat from downhole. Treating the equipment from downhole, it is the most efficient chemical treatments for you or your equipment, because you are treating, you are protecting the tubing, protecting the casing, protecting the equipment, then increasing your running life, reducing your chemical consumption, because the chemical is work very efficient in high temperature, especially if you have some what you call poor point depressants and so on. Treatment downhole, yes, we are injecting chemicals. Some people doing batch treatments, is injecting some batch treatment, batch chemicals, but it's batch treatments, you cannot control. It's not more efficient like a continuous treatment and so on. Some other people, if you have a scale, you need to study what type of scales you have in your wells. If this calcium carbonate or whatever you have, where is the scale is participated? Usually the scale participating if the gas start to come out, if solution, if you are below the partial pressure. Some people, if the scale start to participate near to the surface, for example, 300 feet, 200 feet, 400, 500 feet, you can play with the wellhead pressures to avoid separations of just gas come out of solution at the well bore, and you are reaching to the surface at different pressure and temperatures.
Okay, great. We have many questions, but we can choose to answer them at the end of the session.
Yes.
Okay,
yes.
Thank you.
Yes.
Now we can move to Engineer Gustavo. Welcome, Engineer Gustavo.
Oh, thank you. Let me try to share my screen.
Okay. I think you're already the host, right?
Yes, he is a host, yeah.
Okay. Yeah, I'm working on it, sharing my screen. Give me a second.
Great, yes.
Are you guys able to see my screen? Just want to be 100% sure.
Yes, we can see it.
Okay. Thank you, Dr. Ghareeb. I mean, great introduction. I really agree 100% what you mentioned with the approach on dealing with sand and gas. It's not just one solution that is going to fix all your problem. There is always a combination between separating solids, handling solids, producing it, and being sure you can look everything as an integral system, not just as a one component that is going to fix that particular problem. Same thing with gas separation. You always have to look the entire BHA. What are the parts in your BHA that either is affecting it or creating gas to break out if you are below or above the bubble pressure? And that's something that we're going to talk about a little bit. On this particular case, just to give you a little introduction of what we do, Odessa Separator is a company located in Odessa, Texas. We has been in business for more than 25 years. We provide different solutions to multiple countries, primarily in the U.S., what is called the Permian Basin and Delaware Basin. We actually deal with some on the Bakken, and international. We have operation in Egypt. Several areas in the Middle East like Oman, and we do some business in Canada. We're looking alternative, and that's something that Dr. Ghareeb mentioned, is we have to check everything about all the different type of artificial lift systems that we're dealing. PCP, by example, is able to handle solids better than a rod pump, but there are some limitations also for the PCP. We consider that any artificial lift system is able to handle a portion of sand. The secret behind all of this is try to calculate the right ratio so you can have the total fluid, gas, oil, and water with a combination of sand that is able to handle and allowing this to pass through without blocking either your plunger or having a sticky plunger or destroying your elastomer, or if we're talking about ESPs, being able to don't plug your stages or intake. So we try to focus this particular webinar. Everything was going on downhole. But like we mentioned from the beginning, don't forget about look everything as an internal and integral solution. So we talk about multiple factors, either if we're operating in an unconsolidated degree formation or a consolidated formation. There is different factors that it can affect the amount of sand that is going to be produced. What we're talking about the inflow, the total rate, the critical drawdown pressure that we're using. In some areas like the US, we do a lot of fracking. So based on the number of wells that you have around, either if you have a frack operation or you have a neighbor well that either someone else is fracking, you can have some potential communication, and this could particularly affect the amount of sand that you can produce either in your natural flow stage that now could be a sand issue more at the surface, or the amount of sand that it will go through the pump, and now your artificial lift system will be the one handling. Everything goes back based on how much bottom hole pressure do we actually have and for how long we're able to keep that one to lift that amount of solid and create less damage or impact to your artificial lift system. Fluid velocity is something that is going to be critical because, like we described before, there is going to be that ratio that is going to either create some sandblasting in some cases when you have too much sand and less fluid passing around your stages, impellers, or diffuser, and on the future, that accumulation and that volume, it could cause a broken shaft, or in rod pond, it can cause some worm plunger. Water flooding. There is different applications that we do in multiple countries. In some cases, we got some water flooding applications that you're going to see some consolidation and communication of some of the sand particles that could start to migrate to now the producer well, and in this point, now you're being affected. There are some other factors that you can use, like some chemical reactions, like hydrolysis of water, carbonate reaction, and changes in the capillary pressure. This variation of pressure can cause some sand to be pulled from different formations, and as you guys are aware, we always are dealing with multiple wells. In some of those, either those unconventionals or conventionals, you're going to start producing from multiple zones. So it could be some sand that is migrating to a particular zone, and it was maybe not expected or not that high volume that it can be produced. So I like kind of like this slide just to give you a brief overview about the sand production causes. And when we talk about regular vertical well or just a conventional well versus an unconventional, the amount of the production of perforations on that production zone is going to be different. And some of the vertical wells we're talking about maybe we're producing for a particular zone, either for 100 to 300 feet. Some cases either we have segregating of different segments where we are producing every 500 feet we get some perforations, or based on the depth of the well. On the unconventional, we try to go more vertical until we found that particular zone where we're going to produce, and now we inject a lot of sand with pressure to be able to fracture on this particular reservoir and try to have an even drawdown and more communication and be located in that producer zone and try to have that high initial rate. So this is kind of the thing that we can see a little bit of the difference of how we normally use on verticals or unconventional wells. And we're going to see also how they behave different. When we're talking about conventional well, we get a plastic hole deformation, and we normally see a huge peak as soon as we start that particular well. Bottom hole pressure is high, all the sand try to go through on the initial stage, and after that, that amount of sand or the volume of those PTV or PPN, based on how we're measuring, it become to stabilize, and after that it start to decline. The difference between an unconventional well, we have the plastic hole deformation from the frac sand on the flow back, so we're lifting a lot of sand. We try to find an stabilization frac hit, and we're going to see those waves and those cycles where the well was not producing sand or less amount of sand, and now we are doubling or tripling the volume, and that's where it can cause some issues on my artificial lift system. Those stages, and based on the cycling that you have in your equipment, is going to cause some particular damage. The sand production also can be based over here. We try to show a typical completion area on the Permian Basin. So the wells are normally spaced either 330 feet or some cases just 150 feet from the other wells. So you're going to see some communication in one point, and we're just evaluating a fraction of that particular field. So you got multiple formation, either the Bone Spring, Wolfcamp A, Wolfcamp B, and multiple zones that you're going to start to produce on those particular areas. I love this picture. This picture shows the number of wells that you can see over here on the Permian Basin. So as you guys are able to evaluate, the spacing between those two wells is not that much. And now we're talking about either 1 mile or 2 miles of lateral section on those unconventional wells. When we see a little more of the verticals or conventional, we see a little more spacing because we're actually locating or targeting that particular zone where the well is producing. So keep that one in mind. It's kind of like punching that particular water balloon, and you get to the point that the pressure or the reservoir pressure is going to change based on the stage that you are on that particular life, and you're going to see communication in that field. So this is kind of like a quick video that I got for you guys on how you normally start to do that fracking or those stages of those unconventional wells.
Geologists have known for years that substantial deposits of oil and natural gas are trapped in deep shale formations. These shale reservoirs were created tens of millions of years ago. Around the world today, with modern horizontal drilling techniques and hydraulic fracturing, the trapped oil and natural gas in these shale reservoirs is being safely and efficiently produced, gathered, and distributed to customers. Let's look at the drilling and completion process of a typical oil and natural gas well. Shale reservoirs are usually 1 mile or more below the surface, well below any underground source of drinking water, which is typically no more than 300 to 1,000 feet below the surface. Additionally, steel pipes, called casing, cemented in place, provide a multi-layered barrier to protect freshwater aquifers. During the past 60 years, the oil and gas industry has
it looks like we're having some issues and the video is not working. Just want to be sure.
It's okay
It's
now.
okay now?
Fracture
Okay.
stimulations in over 1 million wells worldwide. The initial steps are the same as for any conventional well. A hole is drilled straight down using freshwater-based fluids, which cools the drill bit, carries the rock cuttings back to the surface, and stabilizes the wall of the well bore. Once the hole extends below the deepest freshwater aquifer, the drill pipe is removed and replaced with steel pipe, called surface casing. Next, cement is pumped down the casing. When it reaches the bottom, it is pumped down and then back up between the casing and the borehole wall, creating an impermeable additional protective barrier between the well bore and any freshwater sources. In some cases, depending on the geology of the area and the depth of the well, additional casing sections may be run and, like surface casing, are then cemented in place to ensure no movement of fluids or gas between those layers and the groundwater sources. What makes drilling for hydrocarbons in a shale formation unique is the necessity to drill horizontally. Vertical drilling continues to a depth called the kickoff point. This is where the wellbore begins curving to become horizontal. One of the advantages of horizontal drilling is that it's possible to drill several wells from only one drilling pad, minimizing the impact to the surface environment. When the targeted distance is reached, the drill pipe is removed, and additional steel casing is inserted through the full length of the wellbore. Once again, the casing is cemented in place. For some horizontal developments, new technology in the form of sliding sleeves and mechanical isolation devices replace cement in the creation of isolations along the wellbore. Once the drilling is finished and the final casing has been installed, the drilling rig is removed and preparations are made for the next steps, well completion. The first step in completing a well is the creation of a connection between the final casing and the reservoir rock. This consists of lowering a specialized tool called a perforating gun, which is equipped with shaped explosive charges, down to the rock layer containing oil or natural gas. This perforating gun is then fired, which creates holes through the casing, cement, and into the target rock. These perforating holes connect the reservoir and the wellbore. Since these perforations are only a few inches long and are performed more than a mile underground, the entire process is imperceptible on the surface. The perforation gun is then removed in preparation for the next step, hydraulic fracturing. The process consists of pumping a mixture of mostly water and sand, plus a few chemicals, under controlled conditions into deep underground reservoir formations. The chemicals are generally for lubrication, to keep bacteria from forming, and help carry the sand. These chemicals typically range in concentrations from 0.1 to 0.5% by volume, and help to improve the performance of the stimulation. This stimulation fluid is sent to trucks that pump the fluid into the wellbore and out through the perforations that were noted earlier. This process creates fractures in the oil and gas reservoir rock. The sand in the frac fluid remains in these fractures in the rock and keeps them open when the pump pressure is relieved. This allows the previously trapped oil or natural gas to flow to the wellbore more easily. This initial stimulation segment is then isolated with a specially designed plug, and the perforating guns are used to perforate the next stage. This stage is then hydraulically fractured in the same manner. This process is repeated along the entire horizontal section of the well, which can extend several miles. Once the stimulation is complete, the isolation plugs are drilled out and production begins. Initially water and then natural gas or oil flows into the horizontal casing and up the wellbore. In the course of initial production of the well, approximately 15 to 50% of the fracturing fluid is recovered. This fluid is either recycled to be used on other fracturing operations or safely disposed of according to government regulations. The whole process of developing a well typically takes from 3 to 5 months, a few weeks to prepare the site, 4 to 6 weeks to drill the well, and then 1 to 3 months of completion activities, which includes 1 to 7 days of stimulation. But this 3 to 5 month investment can result in a well that will produce oil or natural gas for 20 to 40 years or more. When all of the oil...
So just to coming back, I hope you guys were able to hear and watch the video. I know I was checking some comments about some issues at the beginning, but this kind of is like a little schematic of what we normally do on those unconventional wells. So you're going to see a typical either 7 to 10,000 feet deep vertical section, and after that we're going to face either 1 mile, 2 miles, or we're talking about in feet. So either could be another 5,000 to 8,000. Sometimes we see until 15,000 feet where we're completing multiple stages. Each stage now is the spacing that we get from either of the perforation, and this is going to be all my production area that is coming forward. So I'm kind of like taking control, being sure I'm on the middle of that reservoir, and now my production is going to be coming with all the sand. This is part of the kickoff point. That was something that we discussed initially. So this is actually where the well start to be deviating, and we start to either being from 1,000 to 1,500 feet. So just as a good information, we discussed that one a little bit on the video. It was talking about the spacing of the sand after it has been fracturing, but at the same time, the main question is, and it will change based on the area and based on the countries, but in this particular case, to give you a real example on the Permian Basin, so to be able to frac a 10,340 lateral section is normally used, or we normally use around 21 million pounds of sand. Those are the amount that are required to be able to fracture that particular well. So I always do this analogy for you guys. So all the sand is not going to be immersed in your reservoir. There is a portion that is coming back immediately. And what do you guys think is going to happen with the rest? So like Dr. Ghareeb was saying, there is a portion that you can go back and say, you know, I'm going to separate a portion of the sand. I'm going to either allow it to produce. But if you try to filter 100%, your problem is going to still be here, and your filtration system is going to plug, and you have to pull the well, come back, and do a clean out. So he mentioned a relevant part. We're over here just to make business, and operators need that income and the cash flow to be able to support the next intervention of the next well. So we always have to be sure we balance everything on the manner that there is a portion that can be filtered or can be delayed or create a little more homogeneous process that you can allow that artificial lift system to produce the sand. And as I mentioned before about the bottom hole pressure, in some cases my bottom hole pressure could be 5,000, 6,000 psi, which is going to allow me to natural flow my well for at least 3 to 4 months. But in some other cases, my bottom hole pressure could be just 2,000 feet. And it says I have around 8,000 feet vertical section. I'm not going to be able to flow this well, so I need to go with my artificial lift system to create the differential pressure that is going to allow to lift that fluid to the surface. In this case, either we go with ESP or gas lift. So one of the things that we talk about is about the volume of the amount of sand that we use to produce. So in a regular flow back, when you still have more bottom hole pressure, you are able to produce around 30% of the flow back sand. So if you do the calculation, that 30% is going to be close to 6.3 million pounds of sand. If you try to do the number just to calculate how many joint of tubing that will be equivalent, so we're talking about 2,715 joint of tubing. It's almost close to 84,165 feet. And if we compare a vertical well or an unconventional well that we normally use between 7,000 to 8,000 feet of tubing, so we're talking about easy around 8 wells to 10 wells that were able to fill just all the tubing with sand. So I always use this analogy to give you an understanding or a visual understanding of the amount or the volume of sand that you actually are dealing with in the initial stage. This is kind of like two different profiles of an unconventional well and a pattern well, like we showed before, because those are too close and one is going to be connected with the other one. So initial stage, we go back, we drill the plugs, we start flowing this well. Bottom hole pressure is still be high, it's going to be able to allow me to lift some natural fluid, without no problem. At this point, I'm able to go over there until my maximum peak and start depleting or declining this well. In this case, I am reaching close to 4,000, 4,500 barrels per day, and after that is declining and it goes to the original stage. This maximum peak is the point that I try to predict and try to be sure I can go back, and now either I will allow the well to deplete close to 1,000 barrels per day, and at that point it's not efficient enough and it's easier to go back with my artificial lift system, either my ESP or gas lift, to start producing this well. In this case, this is kind of like the typical. In this case, because it was a pattern well profile, we start with the same initial stage. We try to reach the peak, but we get hit by a frac well. So somebody was fracking right next to this area, and instead of depleting, what actually happened, it was increasing. And you can see, gas came down, but total fluid, oil and water keep rising. And it took longer to be able to deplete this well, around 6 months, compared with a traditional well that it was just 1 mile from this location. So again, like we mentioned before, we have to look at sand management as an entire concept. So we have to understand what can we do on the reservoir. Either I do some reservoir coating sand that is able to hold some of that sand that I use to frac, or formation sand that is coming through, or either I start dealing something on the well on my bottom hole assembly. Either I go with a specialty pump that are able to design that. Either I go with sand management equipment, either descenders, sand screens. We will evaluate that one weight based on the volume and some of the history that we get from the wells. But again, sometimes we're looking the problem just downhole. As soon as we start producing this sand, it's going to be now a problem at surface. So we always have to design, looking the entire picture and being sure, do they have the right equipment at the surface? Do we have the right vessel, the right separators? Do they have enough capacity to be able to hold this volume of sand, or do they need to get some different communication from this particular path or wells that I start to produce, so I can dispose this sand and do the proper treatment? When we go back, either on the metallurgic aspect from the pump, either I go from tungsten carbides, either I use zircon, a ceramic, specialty pumps on the surface, either, like I mentioned, either we use cyclone or desander at the surface accumulator. How do I transport those particles? And how do we handle everything? Either if we're handling that sand problem downhole, either we have to evaluate, do I have to do gravel pack? Do I use premium screen? Do I use sand screen? Do I use descenders? Some of those alternatives, there is a combination. They got some pro and they have some cons. And again, we have to go back and understand the formation that we're dealing and how fast are we depleting this well. Normally, in a typical well, it's not just one problem at a time. Like Dr. Ghareeb was saying, we're dealing with sand, but at one point, we're now start dealing with gas, because that hydrostatic head, that 3,000 feet that I used to have above my pump, is no longer there. So I lose that hydrostatic head, I pass that bubble pressure, and now I'm breaking the gas. It's no more in solution and becomes free. So I'm going to get a combination of sand and gas issues in one point of time. Or depending on the formation, either I'm going to face some scale tendency or some corrosion issues. So I always need to look the entire picture to be able to design the right equipment. At the same time, as it was mentioned on the video, when we're doing those fracturing, now they're able to add some different chemical or inhibitors at the same mix with the water and the sand. So now we can have some inhibitors at the face of my reservoir, being sure I am protecting that particular zone with some corrosion and scale inhibitors from the beginning. Normally, this will last between 6 months to 1 year, but again, sometimes the problem is that severe that I need to use a different company. So this picture, what I want to show you guys, if you have the opportunity to be in a tear down, or if you have the opportunity to be in one of the on location, normally this is what we see when we're talking about sand. We see a agglutination or conglomeration of particles that are just going to be aggregated together because due to the viscosity of the oil, we're going to cause this particular agglutination creating chunks. You don't see particle by particle independent. You always see something like this that is passing through your pump or that is passing through your sand filtration management system that you have in place. So that's a regular question that you guys have to ask yourself. What is the size of the particles that I'm dealing with? So in this case, I can design my right clearance or slippage between my plunger and my barrel, or if I'm dealing with ESP, I can know what is going to be the erosion percentage that I can face when I'm lifting that high ratio, high volume of sand through my stages. So there is a way that you can take this sample, you can use multiple chemicals to remove the oil, you can dry the sand, and you can calculate, you can pass this through different mesh and calculate the retention percentage of the sand particles and have a better understanding of the sand that you're dealing with. Either that's frac sand or is formation sand or a combination of both based on the stage that you are from this particular well. So what are the effects? What sand can cause to your system? So this is our picture from an ESP. This is how normally the ESP looks like after you're dealing with a lot of sand. You see a lot of erosion, you see a lot of plugging in your stages, you see erosion over there, totally plugged. You see some combination between that finer or 100 mesh sand that in a high volume, it could just plug the entire system. So keep that in mind. Either when we're evaluating the economics and we try to lift this well, and we always are checking our budget, if we don't go with the right solution, and I spend all this amount of money on this new well, and I don't design my artificial lift system appropriate to handle that volume of sand, what I'm going to do, I'm going to trash a pump, so I'm going to spend more than 200,000, because regardless that you're leasing the equipment, you have to pay for, and at the same time, I have to pay for the well intervention, go back and clean. So there is a way that I can avoid this type of problem, going back and analyzing this with my services company to mitigate and reduce this damage through my system. Or rod pump. This is picture between your standing valve, how this looks totally plugged. This is the bottom of the pump, totally plugged with sand, and some of the things that Dr. Ghareeb was mentioned before, the damage of the sand that is going to cause on my plunger when it's falling down and it's going to create this effect. I'm going to crush those particles over and over for every single stroke to the point that either I'm going to stick my plunger or I'm just going to destroy it and cause an issue, and I have to go back and pull the well. Another thing that sand can cause is in dealing with a lot of sand in a rod pump well, and it's going to be above my pump, and it's going to start to creating some buckling because it's going to start trapping some of my rods and pulling just to one side, and it's going to create a buckling effect. It start causing some wear on the couplings. It's going to cause some high load system from this particular area where it can cause some fatigue and actually create a failure, and I have to go back and pull this well. So what can we do? There are different ways that you can handle on ESP. ESP is a little more unique because the intake of the ESP is around the system. So I have to isolate the system to be able to control that fluid and sand prior to the intake of the pump. So in this case, either you go back and you have a regular cut packer. The only thing that you're doing, you can do a regular desander, you can do 2 stages filtration, but what you're doing is creating a different flow path. So fluid comes from your perforation, goes through either your desander or your sand screen, and it cannot go up because you have this elastomer that is creating a temporal seal. So fluid has to follow a different path to be able to create that filtration, homogenization, or sand management that you are designing for. Fluid after that will go through the equipment, it will exit out, and now it will go through the pump. That is one of the benefits that you can do with the cut packer, because you can do just one run on the installation. You run your sand management equipment right below the sensor of the ESP. The sensor has a 2 and 3/8 connection that you can set up everything underneath it, and you can put that weight below it, calculating based on the severity of the well, analyzing the dot lead and the inclination to be sure you're not going to cause a different issue. Another method is try to put a mechanical packer, hydraulic packer, but in this one, you have your sand control management underneath it. You have to have an on-off tool, so you have to do two different runs. The first run, you go back with the tubing, set the mechanical packer with all the sand management. You now use the on-off tool to liberate the tubing, so you pull out all your tubing and go back again with your ESP, so there is an space between those two, are not going to be connected. The benefit about this is kind of like creating a better completion system. So you have to pull your ESP either for electrical issues, for cable, grounded ESP. You don't remove your sand control management system. You just pull your pump and come back. Or if you're depleting the well super fast, and let's say it has been 1 year, I deplete this, now I want to use a rod pump because I'm on the right production range, so I can go back just with my rod pump, and this is already in the well. So this is kind of like the benefit in case that your perforations are above it, like on ESP, Dr. Ghareeb mentioned a little bit. When you're dealing with gas, either you go with your pump below the perf, so the gas just keep traveling through the backside. But we got some wells that the perforations are above and below, or just above, and I need to have a sand control management because otherwise I'm filling this out to the point that I'm going to damage my pump. In this case, I use a shrouded system, so what I go with a shroud that is just like a casing, I encapsulate my ESP to change the intake, so now the intake, it will be my sand management system, and after that fluid will go inside the shroud and it will go straight to my pump. Sometimes this is also used to cool the motor temperature. If the perforations are above the ESP, I need to force that fluid not to go straight, but actually to come down and follow this path to increase that fluid velocity and create a better motor temperature. So just to go back and emphasize now, this is an schematic of a completion or a BHA that we can do on an ESP. So in this case, we're going to talk about first, what can we do with an ESP that is maybe able to handle the sand, but either I can have multiple shutdowns, and this particular tool that is called the ESP sand lift, the design is just to regulate the amount of sand that it can go back through your pump when you're facing these shutdowns. So if I don't have this tool and I have a shutdown, all the sand is going through your pump at the same time. With the sand lift, what you're doing in the shutdown, the sand that already was produced and it went through the stages of the pump, now is going to be regulated. So when you're dealing on those shoot downs, instead of getting all the sand at once, you're just regulating that sand volume. And like we discussed previously, you're just creating the right ratio for the particles that can flow inside the ESP. And now your ESP is going to be able to backspin and force those particles to now come out. So this is some of the advantage from this system. It's kind of like help you to regulate. We're going to see a quick video over here. The other benefit that you get over here, you're able to do acid job or some
One of the primary issues in artificial lift is handling the solids during production. During a shutdown, sand in the production stream falls back into the pump and creates a solid plug in the pump. This can cause a failure when turned back on. This failure is costly to operators. Operators need a solution to be able to backspin the pump and treat through the pump with chemicals from the surface. The purpose of the sand lift is not to stop sand above the pump, but to regulate the rate of sand going back into the pump when the pump is shut down, reducing plugging and allowing for chemical treatment from the surface through the pump. P pump turns on the differential pressure created by the pump, pushes the dart sand breaker off of the open landing pad to the top position. Fluid and in-train solids flow through the tubular ports in one flow path to the surface. When the pump is turned off, the dart sand breaker falls back to the open landing pad. Fluid and in-train solids begin to flow back through the tubular ports following the same path. The dart sand breaker and tubular ports regulate the rate of sand that comes back through the pump. Because the sand lift has no seal, it provides the operator with the ability to chemically treat through the pump from the surface and use the backspin to clear obstructions from the pump.
So this is what I was mentioning. You're able actually to either do an acid job, surfactant job, or pumps an inhibitor through your tubing if that's required. You get enough open area that you're able to do that.
When the ESP pump is turned back on, the centrifugal force of the ESP creates turbulence, which lifts the fluid and entrained solids up through the tubular ports to the surface.
So the benefit of this tool is, again, is just being able to handle the particles that already went through the pump, and now you're able just to regulate this volume of sand that is coming back through your pump in a better ratio, that you're able to allow particles to go through the stages without causing a plugging or damaging your system. Or some cases when you're creating either a seal, it can cause some of the gas to be trapped above your ESP that now you're not able to restore. So that's the benefit of this particular tool, is sand management that you can have regulating above your ESP. One of the benefits, this is a better layout of the equipment. You got their own housing, you got the lifting neck. So this goes on the inside. This is a special screen. So there is a lot of open area. You get more than 292 square inches of opening area. You get more than 3,000 cubic inches of volume capacity that you can use for flow. So there is no limitation over here on how much fluid can pass through. And the best benefit, you can actually refurbish the equipment. So one of the things that we use with these particular tools are being able, we get some bolts underneath it, so we're able to remove those bolts, do a better tear down inspection, and just pull the internal components, and being able to refurbish is whatever is needed. But the most important thing is understand the type of sand that is coming back through your pump, and try to be sure you're regulating, and you want to verify that this screen is actually giving you that amount of open area necessary to allow the fluid to go through the pump. So you're able to disassemble and just put it back after inspection through the system. After talking this, like I said before, this is above your ESP, but what can we do below it? What can we do to avoid those particles to go through the pump stages? So in this case, we have what we call two-stage filtration. It's a combination between sand screens, desander. We use the centralizer just to, like we discussed previously, we need to analyze the dotlet and the inclination where you're setting the pump. So the centralizers is just going to be able to reduce some of the vibration from the system, or any cavitation that it can cause this long BHA that is underneath the pump, because everything will be connected, in this case, below the sensor. But the other benefit that we see is being able to reduce some of the harmonic and be sure that the ESP is always centralized, so you're not pulling that shaft just to one side due to the weight of the equipment. On reality, when you're running tubing downhole and you don't use any centralization, your ESP is going to be more close just to one side, either to the right or the left, based on the inclination. But what you try to do over here is keeping everything more straight, so all the length of your ESP and the shaft is going to be straight. One of the things that the company does, we analyze and we do a 3D wellbore view for trying to show the production engineers what is your sensor, what is your ESP. We analyze all the dog leg severity and the inclination to be sure the bullpup or the end of the BHA that is underneath it is on the right section, and we can actually pull the equipment or running that hole with no inconvenience. We have some slotted subs underneath it, like I mentioned previously, is where the fluid goes through. This is more where the fluid is etching out above the cut packers, and all the fluid that is etching through these pores is going to be with less volume of sand. So now the ESP is going to be able to lift those reminder particles that pass through the screen or the two stages. You want to be sure you do enough calculation of the open area from the slots. There are some companies or people that like more perforated joints. I kind of like more slotted section because it's less pressure drop in case that you're dealing with some scale or calcium carbonate, less probability of creating some build up over this area. And if you have a shoot down in some of the sand that you get above the cut packer and you want to flush through the casing, now you're able to flush that sand and being able to send it inside the downhole or sand management equipment that is underneath the ESP. So this is going to work more like a ramp for the sand, so you're able to reduce the amount of sand that is located above the cups, and it's just forcing everything to go internally. This is the elastomers. Like I say, this type of cut packer, you don't have to set the packer. There is no mechanical action. There is no hydraulic action. It's just the OD of the cup of the elastomer. This is 100% elastomer. Is close to the drift of the casing. But how this will expand? Now you have in consideration the hydrostatic pressure is going to cause that pressure to go back and force some expansion from this elastomer. And as soon as you turn off your pump, the differential pressure and the drawdown that you're generating on your ESP is going to cause this bottom cup to expand to create that temporal seal. As soon as you pull your ESP will be off. So this elastomer is not expanded anymore. And the only thing that you have to do is just pull the equipment and you overpass that capacity from the hydrostatic head, so you're able to just retrieve this without no problems. There are multiple designs based on the problem that you try to accomplish. Either you can do a triple seal to be able to have more surface area from elastomer in case that the casing has already some previous damage, either due to corrosion or scale, or you want to reduce some of the high amount of gas that is passing through, that it can cause some swelling around the elastomer. So that middle elastomer, it will give you the right section. The OSI bypass, this is kind of like the safety factor. Every single time that people is working with sand management devices, the main concern is what can I do if the system plugs? Or what can I do if the tailpipe is full with sand? So as soon as something like that happens, this is a secondary intake in the system that is going to give you an opportunity to bypass your primary sand management system that you have done whole, and you're able to have all the fluid with the sand to go through this bypass section. You can do it either with a screen jacket, wider, it means 75 slot, bigger than your traditional filtration, or you can just do with slots around it. But the main point is allow the ESP to don't operate dry and always guarantee fluid through the system. So this will allow you an option to reduce the well intervention, and now the ESP will be producing all the sand, but it's more like achieving the run life of the ESP without any sand management. So let's put some numbers. Let's say that we're able to achieve 2 years run life with this equipment, and now it failed because a scale or some iron sulfide went through and plugged the system. Now you are able to bypass, allow to produce, and in some areas where you have to plan more those workover intervention, it kind of give you an opportunity to understand. If you were analyzing and checking all the sensor parameters, we can see a peak on the PIP, and that's the point that we can go back and say, it looks like the bypass valve was open. We're now seeing some solids at the surface. I know my ESP is dealing with the particles or with the sand. I have to start planning in a workover intervention, or I can do a flushing through to see if I can flush the screens underneath it, and I can go back to the main primary filtration system. Or if that's not the case and it's not possible due to the amount of plugging that you already have on those screens, I now at least know that I'm going to be battling all the solids with my palm. So that's why we say before, there is not just one solution. We have to look everything as an integral system. So I am prepared already that my ESP is able to handle some solids, so I can accomplish another 1 year or 2 year of run lives just producing some of the particles through my palm. This shows that activation process. So my primary filtration point is totally plugged. So now fluid will go through this system. It will reach more than 33 psi. That's the setting point that we have for the spring. So as soon as you reach that, fluid will go through the bypass. It will go internally through the packet. It will exit out through the slotted sub, and now will go through the pump. Again, this is taking a better look of the sand filtration or the sand screens. How do we size that one? Is based on the particle size distribution, and we're going to talk a little bit about that. But what you're doing over here is don't try to filter 100% of the sand. That's the main mistake that has been seen production engineer suffering from, because when they think about sand management, they don't think about being able to produce sand. They think about a system that is just going to filter 100%. If you try to do something like that, you're going to plug the screen and you're going to lose the intake, or you're going to lose your filtration portion, and you have to pull the well. Normally, it's recommending to produce around 30% of the sand based again on the particle size distribution. We try to filter either 50 to 70% based on the well conditions, either iron sulfide or the scale that you're having. But you always want to deal with some minor particle that it can go through. The way that I like to explain this is more like, imagine that instead of now dealing with all the sand that was going through your ESP at the same time, it do a little bit of the same concept like we explained previously. You're able to filter a portion, but at the same time, the remainder of the particles that pass through the screen, you're regulating. You're regulating how much sand can go now through your pump. You know that because we do a particle size distribution, so I can calculate those ratios to be sure those particles are not going to damage my pump. Or in case that I have a rod pump, I can calculate that its leakage or clearance better to don't lose production. And when we talk about that particle size distribution, this is the graph. Like I mentioned previously, you actually take that sand sample, you're cleaning that sand, you're drying all the oil and just drying all the particles to be sure you understand the retention percentage. And we use this other curve that is actually more the cumulative percentage. It's used more with completion screen. We try to calculate the sorting coefficient just to be sure how the particles are going to behave and what agglutination percentage can we see on this particular well. So this is going to help you to get that better understanding of what particles are going to be filtered out and what particles are going to flow through the ESP or through your artificial lift system. To be able to calculate that, there is a simple stage based on the total fluid that you're passing through. That's going to determine the number of a screen. Remember, we want to eliminate pressure drop. If we try to flow everything just through one hole, is going to create a huge pressure drop, and you can cause more problems on the future. So we try to use that target production, and one of the things that Dr. Ghareeb was mentioned, take in consideration the number not just of oil or oil and water, take in consideration the total fluid, including the gas. How much fluid is passing actually through, because it's going to occupy some space on my system. After you get that number, you can actually classify your well if you're dealing just with sand based on average, bad, or severe. That is determining, and there is multiple SPE papers about it, and it's more about the milligrams per liter that you get in solution. After you're classifying that, Now, what you try to eliminate or calculate is that fluid velocity that is passing through the screen, so you're not creating a jetting effect that you can start perforating that screen jacket, and it's that sweet spot where your screen is able to handle that particular fluid and sand, do the filtration, do the regulation of the particles, and eliminating that pressure drop. So this is going to determine actually the number of screens that is required, because this calculation is going to be based on each screen. And as I mentioned about the pressure drop, in this case, with the same 5,000 barrels per day and 5 tubing screen, we see that the pressure drop through the screen is actually 0.84 psi. That's actually nothing if you compare the your traditional intake of the ESP, your total open area base, if you have that screen jacket that normally they have around the intake, or you cut that off and you get just the 3 holes, but you're going to see open areas between 12 square inches until 26 square inches. So on open area, you're talking about on this particular configuration, you can have more than 1,814 square inches. So you're more than 1,000% above this number, just to be sure, because we're doing the right things underneath it to handle that high fluid velocity. Another benefit that you guys are going to see, we talk about erosion and the fluid velocity and the particle side velocity, that means the velocity of the sand. This configuration is going to be able to allow that particle to coalesce around the screen. You are decreasing that velocity and create a different B2 or second velocity internally through the system. So the velocity that is traveling inside on the particle is going to be lower. So when it's passing through the pump, there is less erosion through the system and less erosion around my ESP housing. On the second stage, we see that desander or vortex effect. What we're doing over here is just 2 stages, so not just using the screen. The reminder of particles that pass through the screen are now to be able to be spin up or create a centrifugal force underneath it and be sending the reminder of the particles through the tailpipe. So in this case, it allows me to do a better production of sand management. I am filtering some sand. I am able to send some portion of some batches through the tailpipe, but there is another portion that is going through my DTU or passing through my helix and going straight to my pump. So now I can calculate that ratio and how much fluid can go through without causing that erosion. This is a video where you guys can see a simulation that it was performed on the OSI lab. So you can see we're dumping multiple of the 100 mesh, some 40-60, some 20-40. You can see there is some portion of particles that are outside, so you're creating that filtration. Some particles are traveling through, but with the 2 stages, you're able to spin that sand, and you see this tornado that is what it's doing is kind of like forcing the sand or the heavy particles to go around the walls and being able to have the fluid to travel on the middle. So there is a calculation based on the delta P that you're creating over here and the drawdown from my pump. I can see the elongation from that wave and how fast it can go and how long it will travel those particles. So my fluid can return back through the middle of the system and go straight through the pump with less particles. So again, how this works, we kind of like do an optimization method based on what is required. Either we go with a desander or with the screen, but we want to be sure what is extending the run life and we're able to protect the system. So we're going to protect the system from sand, extending the run life of the equipment, longer time in production, so we're able to reduce our OPEX and CAPEX and being able that we are able to perform better and have better options to reuse that artificial lift system. Possible, try to increase production because sand is always occupying a small space that it could be taken by fluid. And again, it goes back based on the volume of sand that you're producing. And the economic is help improve the cash flow of the project. So instead of pulling a well every 3 times per year, now we're able to pull this well maybe once every year or every 2 years. I mean, everything will be designed based on the criteria that we're using. So for that criteria, again, we come back on the design, either the angle of the helix, avoiding the jarring area, the length of the tool, the material, the type of intake that I have to use. I need to analyze the fluid properties, the viscosity, the density, the production parameters. I need to analyze the pumping speed in case of rub pump, the frequency, the type of pumping unit that I have, because it's going to translate on my drawdown. Either I have a Rotaflex, either I have a traditional 912 unit, the fluid rate, my PAP, and most critical, the solid particle distribution with some of the solid analyzed, so I know if I'm dealing with some waxy materials or if I'm dealing just with fluid. When we come back to design that particular centrifugal force and being sure all the fluid that is passing through that helix, we're calculating the right ratio, and we try to come back to the optimal range. And you guys maybe already have a training or a webinar on designing those ESPs and what is the spectrum that you always try to be so you're not undersized or oversized. We try to do the same thing with the helices. We don't believe that one size can fit all, because all the wells are behaving different, and the amount of fluid that is passing through my equipment is going to change after time. In some other wells that maybe I have some injection and I keep a more controlled rate, and I'm able to keep my production fluctuating for 1,000 to 1,000 or to 1,100 or 1,200 barrels, and it's going to be a small swing. On unconventional wells, on the other hand, my depletion is going to be severe. I can start with 5,000 barrels today. 3 months later is going to be already 2,000, and 6 months later is going to be close to 800. So I'm going to get a little more aggressive depletion curve, what is going to cause my drawdown to change. So what I want to be sure when I sizing the helix is we calculate those fluid velocities, we calculate those portion of particle that goes through the system, and I want to be sure based on the microns, on the size of the particles, I want to be sure in which range I am going to be after I am depleting this well. If I start with this case 400 barrels per day on this particular helix size that it have this particular angle, because all the helices, as you guys can see over here, the opening from the angles are going to be different. So if I'm dealing with just main 400 microns, I can maybe see over here close to 90% efficiency, but as soon as the well is depleting, I'm changing my conditions, that fluid velocity, that particle velocity and drawdown is changing, and is going to slowly start to decrease my efficiency. It doesn't mean that the system is not working. It means you're just losing a percentage of efficiency. There are ways that you can play with the equipment or with your downhole parameters to compensate this, so you're not operating on the low side. We can always either increase the pumping speed just to give it a little more drawdown, or we can always play with the stroke lane to compensate that out. If I'm dealing with ESPs, I always can just increase the frequency, and again, it goes back on how much fluid actually I have above my pump and what is the pump capacity. Same thing with the next one. I mean, you're talking about now between 600 coming back to zero. You always want to find the sweet spot. We did an analysis, and we did several CFD, that is some simulations or computer simulations about those particles velocity and how it's going to behave based on the Baines angle. So as you guys are aware, on ESP they always try to calculate the Baines angle, or the angle between the stages, to be sure you're handling either more solids or some gas, so you have more or less compression ratio internally in your system. On this particular case, what you want to be sure is that jarring area, that is where the fluid is going to be etching out, you're not exceeding a particular speed, because otherwise you can create a sandblasting effect and it can cause some damage. And again, it goes back based on the particle size distribution. How bigger are these particular particles and the jarring area that you get through your system? This is going to determine your efficiency, and it's going to determine again the efficiency based on the angle, based on the type of particles that you're dealing through. And if the angle is changing between 1 and 10, we find out that the changes are not that significant, because we keep the same PAP or the same drawdown. So this is part of the study that we did. You can see on this computer or CFD, you're seeing a lot of pressure coming through. So we're simulating that your intake or the drawdown is coming through this part, either on ESP or rod pump. So you're forcing fluid to travel down due to the differential pressure is passing through that helix, and now that's what you're creating, that centrifugal force. So the particles are going to start hitting these walls over and over 365 days. So you want to be sure you're using the right metallurgy and the right speed. So the red spot that you guys are able to see over here is right this area. That's where we have a high pressure drop and a high speed, and after it's coming over, that is the distance that the wave that you're creating over here, that vortex effect, is start to dissipate. And after that, fluid will come back internally through the inner tube. So we got some charts that we always provide, so you can take decision on the fly, and you're able just to get a baseline of what are the ranges. But again, if you're able to work with your services provider, we can actually analyze more those conditions to understand the rate of sand that you actually are lifting now, where the particles are going to create the radial force effect, and you're causing more agitation, or you have that wave or that vortex. What is the right distance based on the volume of sand that is passing through to reduce some of that erosion? So that's what we bring back the metallurgics that you're using, because it's going to cause some sand penetration where the particles go through the wall, and we're able to see some of the low penetration rate is more when you're able to calculate that fluid velocity is going just to create marks, but it's not going to affect the system. As Dr. Ghareeb mentioned before, and we have been talking about it, there is not just one problem. We always are dealing with corrosion as well. So corrosion is going to start to affect some of the metallurgy, that start to peeling some of the metal and creating some weakness. So when I'm dealing with this penetration, now the problem become more severe, and is going to be more deeper marks through the system, through the point that this can be cut in half. So this is some of the photos that, centrifugal force was not calculated appropriately. You actually create too much efficiency. You did an amazing job sending those particles through the tailpipe, that you cut the tubing underneath it. You can see over here there is still be some marks. You actually cut the tubing, and you damage the threads from the bottom of the system. This is a different view where, again, that calculation was just hitting over and over based on the depletion stage that the well was, and you can see the marks. You can see actually that wave was able to travel over 5.3 feet, and it came down. It was depleting, and it stayed over here close to the 2,000 barrels, and it was hitting this over and over. It was depleting again, reaching the 800. But it didn't cause any failure. It was able to be controlled or retained in their equipment. So we go back based on the design of the material. Either we can do some carbon steel, plastic coated, nickel plated, stainless steel, or a special alloys to be able to control that high corrosion and high erosion rate that it goes through the system. So this is kind of like the analogy where we want to be sure. We want to being able to increase our profit. We're over here just to create some revenues to the company and being able to have a better cash flow. And you can see, based on the type of intake that you're choosing, your sand management is going to be either a little more efficiency or less efficiency. It can work, but it's going to be based on the approach that we're choosing. Either I am taking care more than 70 to 80% of the sand here. Either I go back with an approach that I'm going to use more like a 50-50, and I'm producing the remainder of the particles, or I'm going back to the point that I just want to be sure, in case that I'm dealing with some solids, I send it through the tailpipe. So pumping parameters are going to determine that efficiency. We talked about this already, but this is how we can calculate those out. And we got multiple calculators and graphs that you guys can use as a baseline to take the decision and be sure every time that we're changing conditions, every time that we're changing these drawdowns, we're able to keep in the right spot to don't cause any other issue. And again, I put this picture so you guys don't forget about how the sand looks like, the particles, how it really is going to be after you try the sand, and you're analyzing this particle size distribution because the viscosity is going to be a factor that is going to affect how the sand is behaving when it's going through your sand management, and it's going to either increase or decrease your efficiency. So if you get low viscosity, particles are going to be able to travel fast, so your efficiency could be higher. If you get high viscosity, your efficiency is going to be lower due to the way of the particles are going to behave. Same thing from the angle of the helix. Oh, sorry. And the same thing to be able to, you're using the right pumping parameters to keep on the right ranges. Um, every time that you choose your intake or your PSD, that is the particle size distribution, you either are going to decide I'm going to deal with 100% of the sand, or I'm going to deal just with this reminder of the sand, and I have less abrasive particles that it will go through my system. And again, we already talked a little bit about that, but the two stages, either in a rod pump, that's some of the benefit that you can see. Either just a regular desander. Now we're having all the sand to go through the slotted intake, and it's going to be just falling through the tailpipe. If you want to use a different metallurgy like the boronized, we can do that. We can increase the length of the desander to be sure we're controlling and regulating more the vortex effect to avoid some of the cutting. And this is some of the graphs that we have in this particular paper that we did in 2017, I believe, excuse me, 19. And in this paper, we were just talking about using two stages filtration. That is means the combination between the screen and the vortex, how we were able to actually achieve higher runtime in the wells. And in some cases, you know, it was a grounded ESP. Any system is going to be 100% perfect, but it's just a matter of communication and how you're able to work with your ESP supplier, your sand management supplier, and the operator. That's how we can determine a success. And you guys maybe are already familiar with this when you talk about rod pump. Dr. Ghareeb mentioned there is multiple pumps or specialty pumps. I'm just listing a little bit some of those, like the Sand Pro from Harbison Fisher or the Pampa. You get different far plungers or Louvre plungers, the sand trapper or desanders, discharge valve. There are multiple devices that you can use to reduce the damage of the sand in your pump. Like in this case, it's just to reduce some of the work plunger. And again, that's what it comes back. It doesn't mean that if you use a desander or a screen, you cannot use this. You can always use other alternative to be able to increase the run life. One of the things that I see has been working great for several customers is either the sand flush plunger or the sand diverter from down end, that what it's going to do is going to be able to divert those particles in every single downstroke. Like again, we can have just the desanders, and the difference from rod pump is because the intake is underneath it, is below that setting nipple, we're able to put all the BA shade that is going to be almost similar like the one that we discussed at the beginning on ESP, except that we don't need that mechanical packer. We just allow fluid to go through the screen. That is going to be your primary intake. We're filtering some particles. We're allowing the reminder to go through, and it's going to pass through the secondary stage, that in this case is going to be the vortex, where I'm just going to be able to take care of that reminder of that 40% that I allow to produce. And I'm going to now graduate that one in small batches so I can provide those small percentage to my pump. One of the things that we did, we got another SPE paper that we have with operators where we talk about sand management, how we're actually able to optimize production and able to improve the system. In this case, we're able to change the slippage and the clearance between the plunger and the barrel to produce and handle some of the sand. This is part of the vortex effect, so you guys can see the same thing that we saw in the video, and some of the particles being going through the tailpipe. Coming back to gas, we're going to deal with different flow regimes. Either we're dealing with a bubble flow, with a slug flow, churn flow, annular flow, or disperse flow. And again, it's going to be either it's an unconventional, it's a conventional well, and the pressures, the bottom hole pressure, and the hydrostatic pressure that I get on my system. So base is that is an unconventional well, you're going to get different stratified wave or annular or slugging effect. This is what is affecting the majority of our system. We talk about we have a horizontal well and we have a kickoff point. Normally we try to set our ESPs or rod pumps at the kickoff points to try to get as much TVD we can, so we keep more hydrostatic head from the system. But every single time that you're getting a curve or this lateral section, it's not 100% 180 degrees that you're just getting through, and it's not a perfect horizontal line. You're always going to get those up and downs when they're drilling, what is going to cause some turbulence, and with the inclination, you're just changing the flow regime at that point, that you're just dealing with that slugging. You get hit with these big gas bubbles that it can affect my pump performance. And one of the things, like Dr. Ghareeb mentioned, now is I was sizing my pump to produce 200 barrels. I now need to design this for maybe 350, because with that amount of gas, I need to be able to leave everything through my pump. So this is a lab. This is a test that it was done at Texas Tech in the United States. And one of the things that we can see over here is more that slugging effect that you can see on the unconventional. So we got some slow motion. So normally my well is not filled 100%. But due to the pressure, because I got my perforations in all this sun, that those different pressures that I'm getting from my reservoir is going to allow this section to behave as a wave. And that slugging is just going to have pushing gas over this part and allowing some of the fluid to be submerging over this section. And as soon as I'm passing through my inclination, that is what we call the heel, that's where we see that slugging effect and the change in the flow regime. And you can see the slugging, how severe it's going to be. And this is what I'm setting my ESP on my rod pump. So that's why we mentioned from the beginning, like either I'm dealing with just sand, but in one point, as soon as I lose some of the head, I'm going to start having some difference, and I'm going to start getting some effect from the gas. So again, this is based on the formation, kind of like recapping what we discussed already. As soon as I get that high fluid level, is going to almost push that gas, and everything is going to be more in solution. As soon as depleting my well, and depleting in this case is more the water, now you see that gas is going to start rising up, because I don't have enough hydrostatic pressure that is going to force that gas to be back in solution, and just breaking that out, and now the gas rate is going to be through the roof. So that's what we normally see, that in the initial state my GLR is low, but as soon as I'm depleting this well, my GLR is still start going up, and this is what is going to create a change or an effect on my system. Is I'm dealing with ESPs again. We got the intake around the stages, so whatever is passing through when I'm designing my pump, I try to always keep a high fluid velocity, so I create a better cooling effect from my motor. And how I do that one based on the calculation between the space of the ID of the casing and the OD of the motor. But if now I have gas going through, I'm going to have a poor motor cooling, what is going to cause some issues on my pump, and is going to force me, or for the ESP supplier, to operate that ESP in a gas mode. And a gas mode, what it is kind of like a fluctuation or changes on your frequency. So you're always oscillating your frequency either from 50 hertz to 45 or 40, and you're always operating on that swing to be able to compress and break some of the gas that is trapped in the stages of the pump. So again, fluid velocity, fluid properties, open area, the motor temperature and the bottom hole temperature is going to be critical factors. So I'm able to have the right combination inside the stages to eliminate the gas lock or gas slot or some failures, because we can always have some of the calcium carbonate now building up around my intake. Either could be due to the transfer of heat that I'm getting because my motor, or the poor cooling effect, or the high delta P and the pressure drop that I'm creating through my intake. So how you can detect if you're dealing with free gas? In this case, if we see that the motor frequency is going up and down, this is part of the gas mode that I mentioned before. If you see over here my PAP or my pump intake pressure, these two are going to be related. So as soon as I'm reaching this point, the frequency is going to change. But you can see that motor temperature is fluctuating again. And when you reach more than 150, 160, again, based on the pump design, you're going to shut off that motor immediately and you're causing a shutdown. So that's what you can see, that the frequency went back to zero. And the problem with that is sometimes you can see a lot of gas being trapped in your stages. I mean, you get a lot of overheat. This overheat can cause some scale issues, and this overheat can cause having your ESP to drifting or moving that shaft in a high frequency, and now start to slowing that down or forcing just to stop. So in one point of time, you can cause a broken shaft because you're operating over these conditions. So what are the solutions? There are different things that we can do. Either we can play with a back pressure on the well, we can do some tubing pressure, we can decrease the casing pressure, we can switch, or we can play with the BSD or operating parameter from my drive. I can have my vortex gas separator or upper tandem or lower tandem gas separator. I can have also gas handler to have a better ratio for that free gas to be back in solution. There are different technologies on the market. Either you can use an inverted trowel to have some of the gas to go through the backside and forcing. The problem with that, if you have a lot of free gas, that free gas is affecting already your motor temperature, and you will create a worse problem. That's what either you go with a full encapsulated system to protect that motor. The downside from something like this is that you have to have a recirculating pump to be able to cool that motor and keep a lower motor temperature. The two downsides from those design is you're dealing with sand, you actually are creating like a basket where sand can go inside and it can cause another nightmare for you. There are another system that you can encapsulate just halfway but have your intake underneath it. The benefit of doing something like this, if you can do a better sand management system, and at the same time you can have a gas separation device. So that's one of the things that we recommend to customers in case that they're dealing with gas and some sand. And actually you can have more like a velocity stream to help to keep the fluid velocity high and reduce some of the motor temperature. So this is some of the products that we can provide. That is the Guardian Shield that combine all those principles. This is some of the papers where we have that we talk about the fluid velocity and how we're able to improve those conditions. And this are all the principles that are behind this. We use the screen as a coalescent effect to cause also some agitation. We have some Bernoulli principles on the outside and the inside. We have some Venturi effect. We have pressure drop that we try to use in our favor to cause agitation and turbulence and break some gas. And we have some centrifugal force at the bottom to take care of the solids. So again, based on the casing size, there is multiple changes that we have to do with your ESP, but you can do a hybrid, do like 400 series with 375s. Again, if you're dealing on 5.5, this is part of the encapsulated or the top system from the encapsulated system. So all the weight is coming from these balls that are around the system and is holding on top of the intake of your ESP. This is part of the calculation of how you can determine the fluid velocity on the outside of the equipment, as well on the inside, and all the open areas, flow areas, based on the approach that you want to take. And if you're dealing more with sand, and you cannot use any shrouded system. There is always ways that you can use a regulator to resolubilize that gas and force to be back in solution. So when it's etching out, you're keeping that free gas and you're forcing it to be back. It's more like another gas handler below the sensor. And there is ways to do a Packer type gas separator. Some people have great success with this on rod pump, and we found some alternative to put it on ESP, so we can encapsulate the ESP and using that cut packet style to now have a ESP Packer type gas separator. Rod pump is a similar thing. I know we're kind of like running out of time, but rod pump is, we can see some fluid pound and gas locking. Again, gas can cause actually some buckling, and it's actually decreasing my efficiency because on my upstroke I'm just eliminating the amount of fluid that it can go through, and some of the gas is going to occupy some space and is going to decrease my efficiency. And when I'm operating on my downstroke, now I'm going to see some of the or try to compress and push some of the gas back in solution, and it's going to cause now some of the pounding effect that it can affect on the future my efficiency and my runtime on the rods. So what are the effects of the free gas? Is Dr. Ghareeb talk about this, but it's also going to talk about delay on the valve opening, low efficiency, high power consumption, gas lock, gas pounding, premature equipment failure due to the high stress. And there is different ways that you can predetermine it. This is a slide from John Espinos, that is actually one of the original creator from Theta Interface. You can see your bubble point and what are all the gas pounded effect that you can do with that, and how you can calculate your own efficiency. Either if you want to handle that gas just with the pump, or you want to use any type of gas separator. So if you're able to operate below the perf, you can just have your pump going underneath it. This will be the best gas separation because you're causing a natural separation at this point. The problem with this, if you're dealing with sand, now the sand can fill it at the bottom, and now you have to have a better management system to deal with the sand that is going to be trapped over here. If you're running these above the perf, now you have to have a gas separator method to be able to force that gas to travel to the backside, so you can separate that one from your pump. Again, we talk about something similar like we mentioned on the sand management. We have to look gas separation as an integral system with the specialty pumps, with the pump and speed, with the stroke length, so we can calculate the ratio and having the right compression ratio on my system. I don't want to have my pump tagging all the time, but I want to be sure I get the right pump spacing to eliminate the failures. So we go back with fluid velocity, and if the fluid velocity is less than the bubble rise velocity, I want to be sure and evaluating all the production. What is my water cup, my gas production, GOR, GLR. I need to evaluate my casing size and try to see what is my gas separator and how much gas can I actually handling. And the fluid properties from my system, the RS, the Z, the BG, the BO, and BW. This is going to help me to determine how much gas it will be break by itself due to the changes of pressure, and how much gas can I separate at the pump intake. Plus, I can add the gas separation capacity that I'm designing with my gas separator, and it can give me a better estimate of how much gas it will go through. So what are the principles underneath it? Any gas separator is either a gravitational gas separation, so in the density of the fluid, what you're doing is slowing down the fluid velocity inside the chamber, and either you can have a reverse flow to be able to, by gravitational, separate the two phases, gas and fluid. You can have also some pressure changes to be able to accelerate that fluid velocity and create turbulence on the outside of the gas separator, so you can break gas prior to the intake. And agitation, what it's going to do is some of the coalescent effect. That's another benefit when you want to use sand screens underneath it. This is kind of just to show you natural gas separator below the purse. Modified natural gas separator is you are in front of the perf with your pump, you can run a 20 feet or a 40 feet gas anchor, so you're actually all your delta P is coming from this point, and you're able to break the gas and having just liquid to go through. A poor boy gas separator, when you have to produce above perforation, this is where we calculate that fluid velocity and that is going inside this, and we calculate actually the amount of fluid that I can store per stroke. And so modified gas separator is when you have the opportunity to increase that chamber space to actually being able to hold more fluid, more volume capacity, and increase the fluid velocity on the outside so I can bend everything. Or a Packer type is I can do that so I can actually have a clean or a secondary zone that I can store liquid and for the gas to go through the backside. On 30, one of the best gas separators, if you're able to do it and produce like that, it could be a Packer type gas separator, because I'm going to be able to actually use my casing that is bigger than the chamber to improve my natural gas separation. Another technology is you have to go with a pool boy style is the slotted on top. This one, actually the slot, instead of being on the side like the traditional pool boy, are on the top section, so it would allow a better breakup of the gas. It creates less restriction for the gas to escape, and it will have enough open area that you can produce more than 400 barrels, 1,000 barrels without causing any issue. Now we have to cite the length to be able to compensate that dead space and being able I can break all the gas before reach the bottom of the system. In case that you're dealing above the perforations and you need to go with two stages filtration, or in this case, two stages in the case that you're dealing with sand and gas, we can always use the sand screen with the gas body. So you take care of the sand and you're taking care of the gas underneath it. But the intake is going to be the screen. And this will help with the coalescent effect that we discussed previously. This graph, it will show kind of like the interaction of the fluid velocity and the slugging. So at least what I want to do is increase the fluid velocity on the outside higher than 6 inches per second. So the fluid, I want to be more than 1 feet per second over this part, so that gas will travel free through the backside, and the fluid with the gas that goes inside the system, now it will create a gravitational separation on the inside, being able to handle with less portion of gas, at least just 40 to 35%. So now my gas separator, I'm building enough retention time and volume capacity that I can separate the gas before it goes through the pump. When it goes through the pump, it has the inner tube, so I'm creating a velocity stream where I can compress some of the gas that it was free back in solution, so I'm able to handle that better with my pump. And I can do some specialty pumps also to be able to handle that gas. And this is kind of like the same thing with a Packer type gas separator, same concept, but now I'm able to build this retention time, and it's going to help me to improve my gas separation capacity based on the casing size due to the bigger annular space and the slow fluid velocity that is happening at this point. So gas will travel free through the backside. And again, we can do that one with the screens, without the screen. That will be based on the condition of the well, or we can do like an upper ports just to be able to handle better the gas and improve the efficiency. So that's one of the things that is always recommended to improve the capacity of the system. We got chamber type gas separator. This is more if you want to handle the gas and being able to break that one by sections. This is in case of rod pump. If you want to do with 200 NCF, what we're creating over here is an even drawdown. So I'm able to deal with just 100 NCF over this chamber and another 100 over here, instead of a standard everything through the pump. On the gas vent TAC, this is a new redesign that we did on the TAC, just to be able to allow the system to bend some of the gas that could be trapped in case that you want to run the TAC below the setting nipple, and below this is going to be your gas separator. So it's always to eliminate gas pockets around it, so you're able to bend that gas free through the backside. So this TAC has some ports that we would allow you to do that, and we show some of the open area. Again, I know we run out of time, but on the chemical side, we can either inject the chemical through the surface, and Dr. Ghareeb already explained the advantage and disadvantage, either capillary strain or batch treatment or continuous treatment. But the best thing is try to treat them from the bottom of the hole. So we use a microencapsulation concept that we're able to take the liquid chemical, microencapsulate it in a solid shape, that now we're able to create like solid state chemical bars. Now this is going to be inserted inside the tool, and it's going to be creating a low dispersion. So the benefit of this is you're treating from the bottom up, and this goes below the BHA. So this is actually replacing the bulletproof, and you can store whatever amount of chemical is needed based on the longevity of the well, and you can increase the dispersion pores either 3 feet, 4 feet, based on the ppm that is required per well. And you can have different inhibitor scale, THPS, scavenger, corrosion, paraffin, acid surfactant, deformers, biocide application. And the benefit of being a solid state with the valve that we got internally is going to allow to decrease any contamination or any spillage of chemical on location. So you actually are consolidating and trapping all the chemical inside the tool. And there is some retrievable chemical that you can do in rod pump. You can connect these below the hole down, replacing the traditional gas anchor and being able to treat the well from bottom up. Same thing for gas lift. You're able to use a retrievable tool, and you can refill it as many times as needed with a slick line. There is always opportunities to monitoring, and that's something that you always have to consider. Continuous CWA to monitoring the iron concentration, manganese, CO2. Also calculate the amines, the phosphate, corrosion, the polytag, that is the part of the tracking system, so you can formulate or change the type of inhibitors that you're getting through. So this is a well with high amount of scale that it was with a shrouded system. You can see how everything was plugged with a scale. We did the same shrouded system for a gas separation with the chemical underneath it, and you can see in the comparison with the second video, and after they pulled the well, everything was clean. We didn't see any scale layers that was trapping inside the system. They were able to pull the ESP without any issues and actually maintain the production and increase the run life. This is some of the case studies where you can see the benefit of using the chemical. Again, rod pump, everything is below. And some cases on ESP where you can do sand management system with chemical inhibitors underneath it as well. And over here we show you all the depletion curve that we did for this well, all the parameters. We're able to start for 4,000 barrels per day and start declining back until 700 in close to 2 years. And we were able to track all the iron, all the MPYs. We want to be sure we're lower than 1. We track the iron and manganese, and we achieved 609 days of run life in this particular case. And we got multiple cases similar. And that's what I have for you guys. I apologize that this took longer and I run out a little bit of your time. But I don't know if there is any question or what will be the agenda.
No, thanks, Gustavo. Really, it's a very interesting presentation. You know, it's we need more and more from that. You know, really, it's. I received one of the questions. It says that it's too much for us. That, you know, you can use as a reference. You know, you can back to these videos at any time if you have a problem, and so then we can use it as a reference. You know, in future. So, thank you a lot. Yeah, it's appreciated. And Loma, if you wanted to.
Thank you, Gustavo. Thank you, Dr. Ghareeb. I think already Dr. Ghareeb, he answered some questions in the Q&A box. I will answer we will take only one question for each. Dr. Ghareeb, uh, you have one question is there a relation between gas and bleeder valve on ESP system?
No, usually each one, each things, have different application, When we said gas and competing with the gas and so, breather valve has another function, but gas, I need to separate the gas. I need just, to not allow the gas to bump it to my pump. I need to increase my pump efficiency. I need to increase volumetric efficiency. I need to decrease the problem created by the gas, like cavitations, like, gas interference, like fluctuation of the gas of the amps and so on. No, gas we need to, especially for pumped wells, you need to avoid gas entering to the pump. After the pump, yes, I see some question, they said why I separated the gas, even I need the gas to lift the well. Yes, you need to the gas, you're helping to lift the well, but this will be after the pump. Before the pump, no. Before the pump, the gas, if there is a pump, the gas will reducing your volumetric efficiency. The gas will take some of your pump volumes, then you reduce your volumetric efficiency. Okay, Gustavo,
Okay, that's
yeah.
pretty much it for Dr. Ghareeb. But Gustavo, we have last question. Is uh, I think you answered it now. Is how can I prevent sand from entering the downhole pump? Right?
Yes, I think we covered that one. So, but we can use different alternative, and again, it's going to be more. What is the volume? How much sand do I actually want to filter? Sometimes is and my perforations are above it, and I don't have that severe amount of gas. I can actually just go above my perforations and the particles just will fall down and it will be to the rat hole. But if I'm dealing with gas, and maybe I'm able to solve one problem, but I need to deal with the other one. And that's kind of the point that we have to balance the equation and be sure what is the best on the volumetric efficiency. Either I have to do descenders or gas separators to be able to compensate that approach, because we normally on real life we don't deal with one problem, we deal with multiple problems at the same time, and we have to find the right balance. But I hope that answered the question. There is not like a magic product that you can go back and say use an specialty pump, go with the Pampa pump, or go with sunscreen and everything is fixed. You always have to take everything as an entire integral system.
Okay, great. Thank you so much. Thank you again, Gustavo, and thank you, Dr. Ghareeb. That's we reached the end of our session. So please do your quiz before the deadline. And that's it. Thank you. See you next time. Keep safe.
Thank you.
Thank you.
Thank you. Bye bye.
Have a
Bye.
wonderful day.
You too.
Thank you.
Bye bye. Thank you.